video lecture is talking about cell potentials and standard conditions. This is going to give you an idea about how we can put this at work with balancing these redox reactions and how we can talk about electromotive force. You should be finding this handout that you can print off at home. I'll get it posted on my website for you to look at. First of all, we're going to talk about cell potentials and standard conditions. When we talk about electrons, they're always going to flow from a position of high potential energy to low potential energy. You can think about this being like in a waterfall. Water is going to fall from a high gravitational potential energy down to a lower gravitational potential energy. Same thing is true of electrons and how they flow. So they're always going to flow spontaneously on their own from the anode to the cathode. Remember, anode is where oxidation takes place and cathode is where reduction takes place if there is a difference in potential energy, just like there has to be a difference in heights in order to get water to fall. The electrons are going to always flow spontaneously toward the electrode with the more positive electric potential. So that's going to be the direction of the flow. So you can look at a potentials chart and figure that out. We're going to look at that chart in a little bit. And this cell potential, or this electric potential difference, is what creates what we call a voltaic cell, because there's a difference in potential energies that causes a push of electrons from the anode, from the cathode to the anode. EMF stands for electromotive force. This is the force that drives the electrons through, and that force is created by a difference in electric potential. Under standard conditions, the standard cell EMF can be calculated using a table. Standard conditions are at 25 degrees Celsius. Changing the temperature does change what goes on in terms of the electrical force, the EMF. So when we say standard conditions, that's under 25 degrees Celsius. That's at 25 degrees Celsius. Now, when you look at a potential half reaction or a cell, in this reaction, there's two different parts going on. On this side here for zinc, zinc is happening here with the anode. Anode is oxidation. Notice how the zinc is losing 2 electrons. Those electrons are going to flow from the anode, zinc, to the cathode, across, and be measured by a voltmeter. Notice on this side, this is a hydrogen electrode. This is a standard hydrogen electrode. Sometimes you'll see it abbreviated SHE, S-H-E. That stands for standard hydrogen electrode. And it has 0 voltage. When you look at zinc in this case, its electrons are going to flow across to the standard electron because it has a higher standard reduction potential than hydrogen does. The salt bridge, which carries the charges back and forth, is made up of the spectator ions, sodium and nitrate. Notice how the nitrate is flowing to the positive zinc and the sodium is flowing through to the hydrogen on this side. So you see everything moving with the charges like we discussed in the voltaic cell earlier. The key equation that you're going to want to use is this one here, that if you want to find the electromotive force or the electrical potential energy, if you take the electricity or the electrical voltage from the reduction from the cathode minus what you get from the anode, you're going to find the overall E of the cell. Half reactions are always written as a standard reduction. If you happen to flip one of the reactions, that becomes the oxidation part of it, you change the sign, kind of like in Hess's law. If you change the stoichiometric coefficients, remember when we balance, you have to get the electrons to be equal on both sides. That does not change the standard reduction potential, even if you double it or triple it or put whatever coefficient in front. The more positive the value, the more likely it is to occur in that direction. That helps you ID the cathode. So when you look at the standard reduction chart, whichever one is more positive, that's going to be the one that's more likely to go through the reduction. The other reaction then would have to be oxidation. The lower the reduction potential, again, the more likely it is to go through oxidation. This chart is very helpful. There's table 1. There's also an appendix in the back of your book. I believe it's appendix E, which is very helpful. And this shows the standard potentials for lots of different substances. If you notice here at the very top, reduction, remember, reduction is the gain of electrons. Fluorine sits at the top. And that makes a lot of sense because fluorine is the most electronegative. It's the hungriest for electrons. It's gaining these electrons to become the F- ion. Permanganate, chlorine, dichromate, oxygen, these are all elements that or compounds or complexes that have strong affinities for electrons. Notice how they're all positive. The basis for this scale, or the 0 point, is the She, the standard in hydrogen electrode. That's defined by us as 0. Everything else on this chart is based off of that standard. Go down here to the metals. Nickel, iron, zinc, water, aluminum, sodium, lithium. They don't want to go through reduction. They don't want to gain electrons. They want to lose electrons. So even though they would rather go through oxidation, they are still written as half reactions for reduction potentials. So notice how negative they are. They're very unlikely to go through reduction. They're more likely to go through oxidation. So, using an example here, if you're given in a particular chart, if you're told that you want to find the standard cell potential or the E for it, you can do that even if you don't know both of them off of the table because of that equation that we just talked about. Let's talk about how this works. We have indium with a plus charge going to 3 plus 2 electrons. So indium is losing those electrons. We have bromine on the other side gaining those electrons. So if we look at the chart up above in the lecture handout and we find bromine, bromine has a standard potential of 1.06 volts, and it's positive. So that means it's pretty likely that it wants to gain electrons to go through reduction. We know that the total for the whole thing is 1.046. If you remember our equation, the E of the cell is equal to that of the cathode, what is most likely to go through reduction, minus the E of the anode. How do you tell us the anode and cathode? The cathode is the one that's more positive, or what we know in this case. Notice you can tell in this reaction that indium is losing electrons, so that makes it oxidation. So you can see that it's going to be the anode. So we plug that into our equation. 1.46 they tell us is the overall cell voltage. The cathode we know is 1.06 volts. And we're going to try to find that of the anode, which happens to be indium. I'll just abbreviate E sub AN. So if I solve it on both sides, I end up with 0.40. Erase it. End up with 0.40 volts equals the negative of the electric potential of the anode. Well, I want to solve this for what E is, not what the negative E is, so I divide by -1 on both sides. So when I do that, I end up with the E of the anode to be equal to -0.40. So I'm using that equation and what I know already to help me solve for what happens for that other potential. Now, if you look at a sample exercise here, this is in thinking about 20.4. This is a sample if you are trying to find out what is the reduction potential and you know both of them and how they look. So let's talk about how to set up this and look at it. First of all, we need to identify what's being oxidized and what's being reduced. This is probably a good time to think about splitting this up and how we balanced it. This is already balanced. We're just trying to find the electric potential energy. So we have the dichromate, and then on the other side, the dichromate is going to go into 2Cr3+. That's that half reaction. So notice what they did to try to balance it. The 7 waters went on this side. So then, since they had 7 waters on the right, we had to balance the hydrogens, even as acidic or basic solution, with 14 H pluses over here on this side. And then you had to think about what the charges to be balanced with. This is 14 positives and 2 negatives. So this is a plus 12 on this side. On this side, one chromium is a plus 3, but there's 2 of them, so the total charge here is plus 6. I can add electrons to balance this. So if I add 6 electrons to this side that are negative, then that's going to balance my charges on both sides and make the charge plus 6 on both accounts. So as you look at this, the electrons are being gained on this side. So that makes the chromium to be the cathode, because it's being reduced because it's gaining electrons on the left-hand side. That just is a refresher on how to balance it. So this overall reaction, once you balance it, for that part of it, is 6 electrons plus 14 hydrogens plus the dichromate ion. And then that equaled Cr3 plus the 7 waters. And that is reduction. Now if you look at that table that I just showed you, figure 20.1, it tells you that its standard reduction potential, and this is the cathode, is equal to positive 1.33 volts. So that means it's pretty likely that it wants to do that. Okay, so keep that in mind, 1.33 volts. If you look at iodine on the other side, that's the other half reaction. Iodine is 6I minus going to 3I2. Now notice we don't have to add any waters to this. We don't have to balance anything else except for the charge. So notice that this has a charge of 0 and this is minus 6. So on this side I have to have 6 electrons. So notice how that's different, because now it's not being reduced, it's being oxidized because it's losing 6 electrons altogether. If you look at the standard reduction potential and think about what iodine looks like, its reduction potential is 0.54. But remember, it's minus whatever is happening to that anode. So the E of the cell is equal to E of the cathode minus E of the anode. So we said, remember earlier, it was 1.33 for the dichromate. Then you find iodine's off the table. Its reduction potential was 0.54 minus 0.54. So the E of the cell becomes 0.79 volts. And that's the electrical potential energy of it. So by using that equation, you don't have to worry about whether you have to flip the sign or not. It does it for you if you can identify what's the anode and what is the cathode. All right. So the voltaic cell, here's another example. If you're given the half reactions, you've got to try to figure out which one is going to be the anode, which one's the cathode, based on the standard reduction potential table. So if we looked at cadmium in this case, you have to use Appendix E because they're not all listed in Figure 20.1. You may have to go back and find this in Appendix E. If you look at cadmium, cadmium is a negative 0.403 volts, so unlikely to be reduced. Tin is a negative 0.136 volts. Well, both of those are negative, so which one do you pick? Which one's going to be the cathode? Well, remember, the cathode is the one that's the most positive. Well, out of that group, the tin is the most positive. It's only negative 0.136. So it's going to be the cathode. That means that the cadmium has to be the anode. So remember our reaction, the E of the cell is equal to the E of the cathode minus the E of the anode. So the cathode potential in this case is minus 0.136 minus a negative 0.403. Now, as you put that together and you do two negatives make a positive, that makes the overall value of the cell to be 0.267 volts. So if you can figure out what the anode and cathode is and use that equation, you can solve for any potential that you want as long as you can recognize those. All right, so how does this work in terms of oxidizing and reducing agents? Remember, they're kind of opposites of what they do. Oxidizing agents are the species that are being reduced. So they're the one that are gaining electrons. They're taking the electrons from the oxidizing element. So oxidizing them, the agents are in fact being reduced. That means they're gaining the electrons. They're allowing the electrons to come to them. They're accepting them at the travel destination. Typical trend, more positive the reduction value, the stronger the oxidation agent. The reducing agent, those are the species that are being oxidized. They're losing the electrons. They provide the way to get to the destination. They're kind of like the travel agency trying to get to the island for your vacation. They're providing the electrons to get to that destination. That's a reducing agent. Typically, the bigger the difference in potentials, the bigger the voltage. It's like the difference between a waterfall versus a ditch. A waterfall is usually really tall. A ditch is very small, so you're going to get more flow the bigger the difference. This graphic that you see in your book is really good. Up here at the top, this is the best oxidizing agent is fluorine because it's the easiest to reduce. They're just opposites of each other. Down here at the bottom, lithium, it's very bad as an oxidizing agent. It's bad as an oxidizing agent because it's really tough to reduce. If you go to the other side, fluorine is really difficult to oxidize, weakest reducing agent, but it's easy to oxidize, so it's the strongest reducing agent. So notice that, more negative values of those electropotentials. So if you look at nitrate and silver and you look at dichromate and you look at their values off that standard table, and you think about how they look, thinking about in terms of oxidizing agents, remember that oxidizing agents are being reduced. So here's my kind of general rule of thumb as you think about this, so you don't get confused. The more positive the reduction potential, erase and start over. The more positive the standard reduction potential, the better oxidizing agent it is. So the more positive it is, the better oxidizing agent it is, because it would like to be reduced. It would like to gain electrons. It would like to accept the electrons that are traveling to it. All right. So if we look up these on the chart, and you look at nitrate and what it does with NO3, nitrate has a potential of positive 0.96 when it's reduced. Silver, when you find it on the chart with Ag, it's going to be a metal, and you have to find it in Appendix E. And dichromate is up there, Cr2O7 is positive 1.33. Silver itself does not have a very high one. It's a negative value. So if you're going to talk about oxidizing agent, the best oxidizing agent is dichromate. It's number 1. Nitrate is number 2. And since silver is a metal and it's relatively low, it would be number 3. So just find out the most positive reduction potential, and it's the best oxidizing agent. Friday we'll try to make some more sense of this, print off the worksheet, see how it goes, and we'll keep working through this.